right? Before we get really into the material in later sections. Okay. Most of you are economic master students, first semester, I guess, right? It took me a little bit more actually. I just count 5, 5, 8, 10, 20. Okay, so a handful is missing. Plus there are public economic students here, right? Still? Good. And maybe also students from higher semesters, which have to repeat. Okay, for those, this course is similar to that one held by last year, actually, but it's not exactly the same, right? So, but the tutorials are held by the same person, they are both, and therefore, I think so the change in the professor should not be a big problem. Okay, so econometric analysis. Here you see again the more detailed schedule of our lecture. It's a long schedule, right? And as I already mentioned on Tuesday, the title of the sections and the sequence of the sections follow strictly Davidson-McKinnon, which does not mean that I follow strictly Davidson-McKinnon, right? But this is the book, the textbook, which I which I try to follow the notation and the approach, and some examples are from Davidson-McKinnon, not all of them, but some, this is, if I have to give you one textbook which is most closely related to our lecture, it's Davidson-McKinnon. Yeah. So the sequence of the sections here follow up to section 10 exactly, Davidson-McKinnon. In Davidson-McKinnon, chapter 11, 12, 13, 14, are then more specific on microeconometrics and time series analysis. And as I said already on Tuesday, this is for special courses, right? So there is a special advanced microeconometrics course, or applied microeconometrics course, taught in winter semester, which is even obligatory for public economics students, and nice to have for economic students. And there are courses on time series analysis and, other applied microeconometric courses, which you should go or which you could go in higher semesters. Maybe not in the first semester, right? Because applied microeconometrics and econometrics, these are the two basic courses. Okay? So it's not a problem. It should not be a problem for the economics master students to go also into the microeconometric course. Actually, I would recommend, because it's a nice complementary course, right? It should not be overly complicated because there's a lot, because of course there's an overlap among both econometrics, right? Yeah, maybe you don't want to do that from a big thing. So we have something which I guess is not in Davidson-McKinnon, and that is Rich and Nassau. So these are two methods which are closely related to what we are doing here in the first chapters when we talk about least-square estimation. That is a nice generalization, and it's also up to date because these two things here are very common in machine learning methods. Right? I guess next Thursday, our new junior professor for machine learning, the next professor for econometrics, the machine learning guy, Philipp Bach, and so some of his papers, and he applies a lot of Rich and Nassau in order to analyze these super huge data sets. Okay. So after this, we're well prepared to understand what is that, right? And then you also will see why some mathematicians say that the university introduces a machine learning course, that's just window washing. Okay, it's just econometrics, what they do. Okay, so it's not super old school what we're doing here. It's a basis for the fancy stuff. And finally, there's later some section about model selection specification, because especially for applied work, that's very important. To have some idea how to assess your model. we just often assume we know what's going on. And there's only some, parameters we don't know, we have to estimate, what the functional form and the variables which are relevant in our model. This is all known for whatever reason, right? Because the theory tells us exactly what we have to do, or because of data availability, whatever, this is the only choice we have, so what can we do? So, it depends on the improved application, but in any way, it's important that you can convince the reader that your model choice and specification makes sense. That's an appropriate description of the data. All right. So that's the plan. Yeah? Okay, and we start, as you see, with regression models. And let me, just start the lecture with a few very general words about what's all about, right? So what's the scope of this, and why are we so interested in regression models, and what is a regression model? Okay. So in this lecture, most of the time we deal with situations like this one here. We have one endogenous variable, so one variable that we want to explain or predict or whatever, right? And we know, or we assume, or we presume that this endogenous variable we're interested in depends somehow on a set of explanatory variables, and this is a matrix which contains columns, and each column is a matrix, contains the data of a matrix, right? I guess Leah repeated the simple linear regression model, already Schneider in the quantity pre-course. The simple linear regression model, in that case, X contains just a constant and a single variable. This is why we call it a simple linear regression model, because it contains actually only one interesting guy, one interesting regressor, right? But this, of course, will be generalized in that lecture to a multiple regression model you already know somehow, I guess, from your bachelor econometrics course. Okay, and there's some deviation u, some, random error u, and because, if that u would be just 0, if it wouldn't exist, right, then apparently the relation between y and x would be somehow deterministic, right? So we just could solve for these function here, right? You can think about the linear regression model, a simple linear regression model, then all the data points would lie on one regression line. You could just spot how the regression line would look like. Actually, we would only need 2 points, 2 data points, right, to calculate the regression line. So there is no estimation, there is no econometrics needed there, right? So we also talk about a little bit about the, the philosophies of this randomness of the error. Like G. G is some function, that relates y and the explanatory variables. And of course, in general, that could be a parametric function, so a formula, closed formula. So plug in your axis in that formula, and then this gives you y. Or it could be somehow non-parametric. I'll give an example in a sense where there are no parameters to interpret and guide, but still you have somehow modeled the relation between x and y. If you opt for a parametric model, then of course there is a choice of linear versus nonlinear model, and most of this first section here on regression model is to convince you that the assumption of here we typically made that this parametric functional relationship G is actually a linear relationship, so that we have a linear regression model, as we call it, that this assumption is not so far-fetched. It's very plausible, a very natural assumption in many applications, and it's not so restrictive as it seems to be, right? Because look, we start with a very general function, maybe even non-parametric, right? And then we talk so long and so extensively about linear models, right? This sounds old school and very restrictive, but it's not. Let me convince you. All right. So what still to say here, yeah, you might also say, well, that's a very restricted view that I'm only interested in only one endogenous variable, right? The label apply off, the rate of inflation in, and so on, right? Isn't it more interesting to look at several endogenous variables simultaneously, right? Well, in that case, you are in simultaneous equation models, and this is one part that we skip here, just for time restrictions. I decided to skip that section and then one of the others, because my experience is that in most microeconometric applications, people are not interested in feedback relations between several endogenous variables. They're just interested in the school success of kids when when there's a switch from G8 to G9 schooling or something like that, right? And not in the like in the macroeconomics, right, where we have inflation and interest rates and output and everything depends on everything, right? You see, a set of several endogenous variable and simultaneous feedback relation which complicates matters, this is in most cases a topic for macroeconomics, and they work with time series. So when you are interested in this, go next semester to time series analysis, and then more or less we talk all the time about how to identify those endogenous variables, these relations between endogenous variables. Oh. Okay, this is why I skipped that. And we focus on a single endogenous variable and not on a set. Okay? All right. Okay, here's a nice slide. So this is a scatter plot from a data set. I guess we uploaded it on Blackboard. It's a rather famous data set, I've learned, about Boston house prices or something like that. Currently, it just works as a workhorse for us. Every now and then I show you pictures, right? But actually, I don't talk about the economics here. I don't, actually, I'm not interested in what does it mean. That stuff, it doesn't matter. What I want to show you is here. Look, here is a scatter plot of a data series. And you see here two ways to model the relationship or to capture the described relationship between these two variables, right? Here, obviously, we assume that the relationship is linear. And if you look at that picture, you immediately see that, you can use this example to discuss the pros and cons of linear relationships, right? The pro is obvious. It's easy, right? It's also easy to communicate, right? Economists' job is often to communicate with non-economists, politicians or whatever, right? The public, okay? And then you have to be simple, transparent, okay? Don't be too complicated, otherwise people stop listening, okay? Linear models, if this goes up by 1 unit, then this goes down by a blah unit. The slope of the regression line, that's easy, that's convincing, right? So that's obviously a plus from assuming that the relationship is linear. All right? Comparing this here, I'll say a few words more on that here. This is one parametric model. Obviously, this here, Vidi-Vaggi line here describes relation better somehow, right? It's closer to the points, But, it depends what your story is, right? What message you want to convey, right? If your aim is to convince people, politicians, the public, that if this goes up, that goes down, maybe this is the right picture. Maybe you shouldn't show that. Because then they ask questions. What is this? Why is it waggling? Where does it come from? Right? And this is not what you want to talk about, right? It undermines the credibility of your analysis and of your argument probably. All right? So in many applications, that's great to have a linear relationship to assume it. Okay, that's a pro. But if you look at that picture, what is a con? Suppose you write a master thesis on the relation between this and that, whatever it is. And your empirical model would be this one. What would be the response of the econometric professor? Good job. What would you say? What's the problem? Yeah.
It's too simple.
Yeah, why?
Because it assumes a linear relationship.
Yeah, obviously, yeah, but how can you see what would be your critical point here? Where you would say, come on, that's not a linear relationship. Where do you see that? Yeah.
Looks like heteroscedastic aperture.
Heteroscedastic would mean that the fluctuations around the regression line somehow depends on maybe on the level of a variable or on time or so. Yeah, what you see is that obviously the deviations from the regression line are larger here and larger there. But remember what heteroscedasticity means. It's about the variance, right? So heteroscedasticity says the fluctuations are larger. But is here the fluctuation? Come on, if I would show you this as a nice description, appropriate description of the relation between these two variables, would you say, yeah, you know, I'm a bachelor, I have a bachelor degree in economics and I study a lot of econometrics and I can assure that this is a good relation? Or would you say something else? Yeah?
You cannot really use the analysis for values that are away from the average.
Exactly. Look here. The point is, you know, and with heteroscedasticity you were close to it, right? You see here a systematic. So, of course, you know, if you have a scatter plot and you put a regression line, there are deviations from the regression line. Yeah, of course, right? But the point is, are these deviations systematic? Do you see an obvious systematic way how they deviate? And here you see that the description here at the end is particularly bad, right? But even worse, you know, it's not only that the description of the data is particularly bad at the end, you know, these points here also lead to, look at this here. Most of the data points are below the regression line, obviously, right? And most of these are below the regression line because some of those extremes are above. This is what just equilibrates that out, right? Linear regression means that the sum of the absolute residuals is 0, right? So if you have here large positive ones, somewhere the negative ones have to show up, right? And here you have lots of small negative ones, right? To equalize the large one here. Okay. So I would say what you see already, well, come on, this relation is somehow U-shaped or something like that, right? This is really rough to go with a linear regression line. But you see, you know, pro and con, there's always a trade-off, right? If you now say, you know, we already talked about the pros of a linear relationship, right? Easy to communicate, you know, but, you know, maybe what you want to say, maybe what you want to talk about is less simple, yeah, needs more sophistication, you know, and then you might say, maybe this is a wrong model. Maybe it's a wrong functional relationship, linearity. All right. Okay. In a parametric way, what would be the next step? If you don't know about non-parametric models, which might actually be the case, right? So, what would be your strategy here to improve things?
Probably add more variables that maybe
Which
capture
variable?
dynamic. I mean, I don't know what the economic variables are.
Only
but,
two, you have only two.
But
There's only these two.
there don't exist any more variables
Yeah.
in the data set.
You don't have data. This is the relationship.
Then maybe I introduce a squared variable.
Yeah, that would be my choice. Look, it looks like this. You know, this is a square. This is a, right? So you learned in econometrics bachelor, I hope, something about the reset test, for example. Don't know whether we repeat that here later. Maybe in the specification assessment thing, right? Yeah, if you would, what the reset test does is, if you remember, you estimate this linear regression model, you take the estimated residuals and then you regress it on the regressor again. And then you will see, right, the residuals, the estimated residuals are particularly large if this is here large, right? And that is not random anymore, you know? Okay, so there are good reasons, right, to say this is not a very sophisticated model. Yeah, obviously not, but it's also a model that has its weakness, right? Each model has its weakness. Maybe for some indications, the weakness here is too weak, right? The problem is too strong. Okay, so, but, you know, we just want to talk about, you know, whether we want to use linear model or not, you know, and here you see the other extreme, in a sense. A non-parametric model, and you immediately see the pros. Much better fit, right? This systematic underestimation here, or no, overestimation here, sorry. Overestimation here and underestimation here at the two ends of your data set. This is obviously not the case here, right? Yeah, and you might say, I've learned more, you know? What this non-parametric regression line tells you is that, well, actually there is no systematic relation anymore if L star, whatever that is above a certain threshold, is sufficiently high. You see, then there is more or less a horizontal regression line, and the same thing for very small values. So the slope of the regression line is dominated here by these guys, which is okay because this is the majority of data, come on, right? But you know, it's still for these guys, because of these, let's say, extreme observations, it is somehow shifted upwards, which is not nice. The slope might be very similar, by the way. You know. And if you're interested in the slope, maybe that's not so big issue. Okay, I don't know whether we spend much time on nearest neighbor regressions in our nonlinear regression setup, but just, you know, have you ever heard from that? Nearest neighbor regression? The name is actually very suggestive. In a linear regression, you use just all the data to estimate, to estimate that point on the regression line. You use just all the data, and you treat all variables, all data points the same way, right? You don't say this is less reliable than the others, or something like that, right? Nearest neighbor means, obviously, or it allows for a nonlinearity in relation, but it assumes that the relation is linear close to my point, right? So it's a local regression. You say that, well, when I want to make a prediction, for example, for this point here, then I don't make use of all the observations, because I say, come on, you know, this data point or that data point, it provides practically no reliable information for the behavior of this data point, right? I'm only interested in observations which are close to that point, which are neighbors, nearest neighbors. So I say, all right, what I'm doing, I'm still doing a linear regression, but now, to make a prediction for that point here, I only use observations which are close to that point, right? So I have a lot of linear regressions. For each data point, each has its own linear regression, where each data point uses only points which are close to that one. That's it. Okay, so you see already the math. If I understand what a linear regression is, I also understand what a nearest neighbor regression is. Because it's just a local linear regression. It's a little bit more sophisticated because, okay, in practice, of course, in practice everything is more sophisticated than in theory, right? In practice, you have to determine, for example, neighbor, what do you mean exactly? An observation that is sufficiently close to that? How close? You have to tell the computer, right? What do you mean with close? This parameter, which determines what close means, is called, you know that? The bandwidth. Bandbreite in German, the bandwidth. So you tell the computer, okay, for that data set, for that regression, with nearest neighbor, I mean this one, or that one, right? And you see if you have the extreme wide bandwidth, you're back to the square regression in the linear thing. The smaller the bandwidth, well, what do you say? Okay, so obviously, if I use all the observations for estimating the relationship, then I'm back to square one. So if the bandwidth is infinity, so to say, I have just a standard linear regression, right? The bandwidth has to be, it shouldn't be zero, because then I have only one data point for regression. No, that doesn't work, right? But if I get in closer, if the bandwidth gets smaller and smaller, how does the resulting, so what effect has this for the resulting nonlinear regression time? What would you say? Yeah?
It's kind of playing connected dots probably. So kind of moving very close.
It's getting more wiggly, right? So this is super smooth because I need all observations. The smaller the bandwidth, the more variation in the slope of the regression line is possible. All right? So if I would lower the bandwidth that is assumed for that, I have no idea what was the bandwidth for that one. But if I would lower the bandwidth, if I say R, lower the bandwidth, then this would get here more wiggly and here more wiggly. The regression line would try harder, to follow the points somehow. Okay? So it has more variation, right? It's less calm. Better fit, but even harder to interpret, right? Well, the bandwidth is one thing, but what it makes more sophisticated from an econometric point of view is something we call kernel function. The kernel function weights the observation within the bandwidth. The kernel function says, okay, the closer a data point is to the data point I'm really interested in, the more weight, the more reliable is that information, right? And the farther away, the less reliable. So it's more or less a weighted linear regression that I use, right? That makes a lot of sense, right? That's the kernel function. So if you run with R and non-parametric regression, yeah, you will probably ask for what's the kernel, what's the bandwidth, right? I'm not an R pro, in EDUs, for example, in more applied work, the applicant is the empirical worker, the software already suggests the standard values, right? If you have, this is why I used to use EDUs, more application-oriented programming in bachelor courses, for example, right? Because all these nitty-gritty details, are just implemented in an okay way, right? And don't know what R does, right? Yeah, okay. Well, I've talked a lot about non-permanent regression. That was actually not my aim, right? But you see, this is, we could have a lecture on non-parametric regressions, but this is the alternative way to think about it, and it's not a better way. The statistician would say it's obviously better because it's a better description of the data set. But yeah, but come on, we're economists and we know what the trade-off is, right? I don't know how to use this here. Okay, so The next slide, which I want to discuss in order to convince you that restricting the attention to linear model is not a big thing, is that one here, and that you might know already from the bachelor, because Cobb-Douglas functions like this here are very often used in the bachelor course. In the master courses, maybe CES functions pop up, which are just a straightforward generalization of these Cobb-Douglas functions. You know why these are so popular? Remember? Can you remember? Yeah, why?
No, I mean, I remember the function.
Yeah, you remember the function. That's good. And they are used for production functions, for utility functions. And then when it's not just a linear thing, economics professors, especially in the bachelor, use Cobb-Douglas. And why? Just as a reminder, it's not a critique, it's just a reminder. Don't forget to ask why, right? I talk a lot about why. So why we're here, what we're doing, why we do not this and not that, And when I say, oh, this is a very common why don't you know why, right? So ask yourself, be a critical scientist, right? Just do not consume something and say, yeah, Cobb-Douglas, for whatever reason. It looks strange, but they always use it, so for whatever reason, I don't care. No, you should care. Okay? So, are you just too shy to say it? Let's assume you're too shy. It's because these numbers are the elasticities. Cobb-Douglas functions are the only functions with constant elasticities. So where the elasticity of output to labor, I increase this by 1%, how many percent does it increase? Beta. Right? Cobb-Douglas functions are the only functions where these elasticities are constant numbers. Alright? And we just want to talk about elasticities, right? And not that the elasticity depends on this and that, right? Very similar actually to this one here, yeah? Then you just use the Cobb-Douglas function. When you know elasticities and you want to talk about the elasticities are constant. It's just a pattern. Okay. This is obviously a nonlinear function, and if you're interested in the elasticity of output and labor, beta, then how to use that, in a linear regression framework, obviously the solution is just take logs. You take the log of the data, you see that you can easily linearize these multiplicative functions. Okay? So, saying you can't use linear regression because there are so many multiplicative, complicated, complex relations out there in the world, this is not true. That's not a good point, right? Because many non-linear, multiplicative, complicated things are easily transformed in linear models. And then we just make a linear regression in the log of the data, right? And again, although it's micro or macro or whatever, you see that the elasticity is just the log derivative of Q with respect to K. Okay? So it's the slope of the regression line in logs. Okay, so that's another good reason why it makes sense to talk so intensively about linear regression models. All right, a few words about the randomness of U. So we talk about statistics and randomness in chapter, 3 or 4 in the work. So the starting chapters are very mathematical, a lot of matrix algebra, right? Because we just, abstract from that additional complication that there's something random going on, right? So why did we do that, right? So philosophically, you might say that the randomness of that error, of that deviation from the relationship somehow reflects our ignorance of the details of the economic mechanism, right? So if you have the idea that in principle everything is deterministic, right? So if I have enough data, enough computing power, enough knowledge, then everything would be somehow deterministic, right? It's like if you throw a dice, right? This is a standard example in statistics for randomness, right? Throwing a dice. Probability of 1 over 6 and so on, right? But if you have a supercomputer, and cameras, you might see the way I throw the dice, you might, have a very good prediction what kind of number comes out at the end, So from a superior perspective, throwing a dice is also it's not random, it's somehow deterministic. It's only that we can control for all these small reasons why the dice rolls to 1 and not to 2 or 3 or 4 or 5 or 6. You see? So this, I remember, that I guess Einstein has big problems with a new quantum physics approach. That's where things are random, jumping around, because he said that his famous quote is God does not throw in dice. Yeah, so in German it's better, it's Gott würfelt nicht. The left original quote, right? Because he has problems with it, right? Saying that, yeah. But anyway, it's a very practical approach, right? Because actually we're not interested in all these nitty-gritty details, right? And if you remember, coming back to that throwing dice example, assuming randomness is an extremely good way to describe what's going on, right? If you make predictions about what the result is, about the variance, about distribution, if you throw the dice 1,000 times, this randomness assumption, although in practice it's actually not random, but the randomness assumption is extremely successful in predicting the outcomes, right? Similar here. All right, but details of the economic mechanism means, already suggests that what we somehow neglect, what we ignore for whatever reason, maybe because we don't know, right, or because there is no data, that this is not overly important, that there is no systematic bias because we ignore or neglect these additional details of the economic mechanism. So a very natural assumption or requirement even, when we talk about linear regression models, is therefore that the expected value of this error, of this deviation of the model, conditioned on our observation x, has to be 0. Right? Though later we will call that exogeneity, right? So you see what the interpretation is immediately clear. It means that, well, on average, right, the effects of neglected row cancel out. Yeah, we have positive deviations, we have negative deviations, but there is no systematic error. There are no systematic errors. Look, this is important to understand, right? That this condition on x, that's important, right? So suppose you are an economic forecaster. You have an economic forecasting model for, output, right? You have regressors x, you have leading indicators and whatever you have in your sophisticated regression model that you use to predict output. That's your job, right? So, but then if you look at the data, looking at the averages, you know that, on average, somehow the average of the error is 0. So on average, the number of periods where I overpredict output is the same as I underpredict, right? So that would be the unconditional expectation. Just show me your forecasts, I compare with the actual values, take the difference, these are obviously the errors, right? Take the average, it should be close to 0, right? It should not be that you have in 20 years, 90 years, you overpredict and only one you underpredict or something like which actually is one test whether a forecast is okay, right? And guess what? Many forecasts have problems, to go through this very small test, especially when the forecasts are political, right? So I've never heard from a finance minister who were overly pessimistic about future output or tax income or something like that. There are always bad surprises. I guess always, right? So these forecasts are obviously not made by econometricians. All right. So, but it's even more than just the expected value of U is 0. It is expected value conditioned on x. Though what we want to know is, well, okay, look, you have this sophisticated forecasting model for output, but now let's look at the errors when the weather is fine. Okay, given x. X, the weather, is one of my, any other variable, is one of my regressors in my predictive model. And now I want to check whether the errors depend on the level of the weather. Yeah. Bad example, but okay. Right? Some variable x. And if you check, and if you find whenever there was a lot of rain in that year, I overpredict, and when there was not rain, I underpredict, then obviously there is some problem with the model relation between rain and forecast of output, right? Obviously there's a deficit, there is a problem with your model, there is some misspecification, something is missing, right? So therefore we suppose or assume or restrict our attention to models where we assume that the expected value of this error conditioned on x is 0, right? So it's very hard, to show, obviously your model is stupid. All right? Look here here's an example for a stupid model. It's not a stupid model, it's a model that could be improved, should be improved. Look, suppose your true model is like this. So actually it's a quadratic model. Yeah, obviously I was inspired by this parametric, non-parametric example. Suppose your model is actually this one. But for whatever reason, right, you ignore that square term. So you just regress y on x, leaving this out. And we know what happens, right? This is the so-called omitted variable bias rule, which will show up, right? We leave a variable out that should be in the model. And is that a problem here or not? Without looking at this here. Remember your bachelor econometric thing. In which cases are they, or put it like this, are there cases where omitting a variable is not a problem? Yeah?
If the covariance between the variables is quite low.
Let's say 0. Yeah, when they're uncorrelated. When you have two regressors and they are uncorrelated, then you can omit that, and this parameter estimation is hardly affected. Alright? The omitted variable bias is induced by the correlation between the variable which are in the model and those you have omitted. That's important. Yeah? Look at the formula, you see, it's a correlation between the variables. If this is 0, omitted variable bias collapses to 0. Okay, and currently, if x is a positive variable, right? If your data consists of positive values of something, then this increases when that increases, and vice versa. Then obviously xt and xt are somehow positively related, though there is a positive correlation, right? So, in here, obviously, look, if I omit this, ut here is obviously nothing but here vt plus that one, because we know this is a true model. And if I neglect this here, then my ut here, the error in that equation, which I estimate, is just actually this. And then you see The expected value in that regression, the expected value of ut conditioned on xt, so I know what xt is not 0, but is beta 3 xt squared. Right? Because I know xt, it doesn't cancel out, and this is, well, probably not 0. Okay? So if this does not hold, we will later see that we will really run into deep problems in interpreting the coefficients if that exogeneity assumption will not hold. But you see that if you look at your data and if you find something like this is also a sign of misspecification on the model. Something is missing. All right? Okay. So, very important assumption here. All right. When we talk about regressions, this is the upshot of that, the major takeaway of that slide. We mostly talk about conditional means. So like here, expected value of u given x. So why that? Look, remember the very first slide about the unknown relationship between y and some expected variable x. What we actually after is, yeah, something like a prediction for y given x. Yeah? So we want to forecast the value of our exogenous variable given our explanatory variable, and because it's a forecast, it gets ahead, right? And a very plausible, or the most plausible aim function, goal function, we assume here in econometrics is that we want to choose this prediction function the way that the expected square deviations from our prediction and the actual values is minimized, is small. Right? So we make a prediction, and of course we want to make the predictions such that the prediction errors, which are just the difference between these two, are small on average. Or, more forward-looking, small in expectation. Right? If your job is to forecast future output, you want to use a forecasting model where you expect that the forecasting error you will make a forecast error, of course, but that forecast error should be as small as possible. Right? Very natural section. Small as possible, now we can talk about what does it mean, small as possible. Right? Obviously, small as possible does not mean just minimize y minus g, because that could be negative, right? And small as possible then be minus 20, minus 30, minus 40 is better. No, of course, it makes no sense, right? We don't want that negatives and positive errors cancel out, so that a huge positive and a huge negative error, and on average, I'm fine. That's obviously not what we're after, right? So therefore, we could take absolute values, yeah, which would make this somehow nonlinear and complicated, right? Or you just take the square, and then positive and negative values. Yeah, this is the same idea. Yeah, you are used from the least square regression logic, right? You don't minimize the residuals, you minimize the sum of the square residuals. All right, one can show, right? This is math, boring math. That this optimal prediction function is always given by the conditional mean of y. Well, this is why we work so much about conditional means, right? So I skipped the proof. You can check if Davis and McKinnon. I don't have the impression that you are involved about that. It's not long. But here's, let me give you some intuition, that you're already used to that somehow. Right, from statistics 101 actually, onwards. Suppose you have n data points and they're coming from the same population, right? And you want to make a prediction of that. So the best prediction is obviously, it's not obviously, but we show here, right? The best prediction is a conditional mean. Look, if you're interested in this optimal predictor, and if your aim function is that your optimal predictor should be particularly close to your data, right? If you now take first derivatives and solve for x hat, you see x hat is just a conditional mean. you're used to that. Minimizing squares goes to the conditional mean. Okay. Centrality property of the mean, you know? All right. Okay, so let's summarize. In the next chapters, we talk a lot about the linear regression model, right? So it's like this. So, and our functional form here, right, which is, when we talk about the linear regression model, obviously just x beta. X is a matrix of the regressors, beta is a vector of the coefficients that are related to the various estimator variables. Then this is just the conditional mean of y given x. Just a reminder. So this is what it looks like, right? So we have one endogenous variable, this is y, and we have n data points for that. So we have a vector of n observations, and we have k explanatory variables, x. And for each of these, we have n observations. First explanatory variable, second one, third one, case one. And this here is for the constant, right? You remember simple linear regression, it would be. In a simple linear regression, then the matrix would stop here. Okay. Then we have k plus 1 parameters, and these are actually the numbers we are after, right? So this is observable data, this is observable data, this is unknown to us. Okay? This is the job of the econometrician to exploit information contained in the data to get some information about betas. Right? So beta 0 would be the constant in our regression, beta 1 would be the slope for the first variable, for the first regressor, beta 2 for the second, beta k for the case 1. And here you see the n errors, residuals, we call them, for each observation, and there is 1. Okay? If you are not used to matrix algebra, yeah, it's very helpful when you start with that to write the dimension. You know, if you're a pro, of course, you just use that, right? Because you know that it's n times 1 dimensional vector, so you don't have to say it. But if you're learn to deal with matrices, it's a nice practice, a nice check for you whether these matrix products here are all well defined. Because remember, I can always multiply two numbers, but sometimes I cannot multiply two matrices because the dimensions have to fit. When I introduce matrix algebra in the first semester maths, in the bachelor, well, I often do this here. So the dimension is okay, the matrix multiplication is well defined, if the length of that vector fits to this dimension. Because you multiply this out when you put this vector on that first column and then on the other column to get your results in T. Okay? So if you're not so sure anymore, it's important for the next weeks. Yeah? Extremely important. This is a technique we use now in the following weeks, at least. Matrix multiplications, matrix algebra. Right? So I don't want to have here a math lecture, right? But this is the technique we use. All right, and yeah, well, of course, this is much more harmoniously. Well, nicer, if you want to work with that formula, this is here. This here is just writing it in a more condensed way. This is what we do when we write this down. Okay. Well, coming back to the slide. Yeah. So, okay, we already used this vocabulary, right? So, y is a dependent variable, dependent endogenous variable, they're also non-loose. Okay, we interpret these data points we have as a realization from a population, right? Remember, when we do statistics, we always have the idea that there is an unknown, maybe infinite population out there, and we just grab a sample randomly out of this unknown population, right? And you can talk a lot about, well, how to pick that sample and how important it is that this sample is actually random, right? So, yeah, selection bias and all these things, you know, that we can talk over these points, you know, when it pops up, right? But you've heard from that problem already, right? So that if the sample you base your regression on is biased because there was self-selection, then everything breaks down. All right, so this is just assumed away here for a moment. We have a realization of the population, it's random, sample size is n, this is the row vector, okay, yeah, this is what we just what I just showed you with this matrix, yeah, A1 from the regression. Well, all right? Okay. Here's the illustration. In Econometrics 101 in the bachelor, you know, where we start with a simple linear regression model, and we talk a lot about the simple linear regression model. One reason why I love to talk about the simple linear regression model is because the pictures are so easy, right? You have really a data plot and a regression line, and you can talk a lot about the regression line and whether there's a bias or not. In principle, you could do that also for multiple linear regressions, but yeah, only in principle, right? Because even if you have two regressors here, x1 and x2, it already gets, you know, it looks like this. It is somehow three-dimensional, right? And you see that everything breaks down somehow, you know, this visual intuition breaks down if you have more than two. So then it gets 4 or 5, 6-dimensional, right? So, but here nice, you know, if you like these pictures, you know, here's one. Okay. You have two regressors, here's the endogenous variables. Here you see the data point, and you see these red dots here are now points in the R3, right? R to the power of 3. Three-dimensional. If you make a linear regression of y on these two regressors, what you do is, what you obtain after this is, and of course we talk now in the next slides how to obtain this. You don't have a regression line anymore, this would be one-dimensional with simple regression. You have now a regression plane, right? Because it's two-dimensional. Two regressors, two-dimensional. Yeah, but in a way, you know, it's the same intuition as in the simple linear regression model with a line, right? So this is this plane here wants to mimic these three-dimensional scatter plot as best as possible, and the deviation from the data point to the plane, that's our u, our error, and so on and so on. Okay. Okay. Okay, if we do regression analysis, which we will do in the next chapter, then, as I said already, if we assume that the functional relationship is a linear one, so that ye is some matrix x times beta plus u, or for observation I, you can write it like this, right? This is observation, this is for observation I. Then the only task that remains is to provide an estimate for beta. So, and because it's an estimate and not the true parameter, we don't know, the estimate gets ahead. Look, not only the beta gets ahead, only also the u gets ahead. Because if we know u, we also know beta, right? So the u is also unobserved, right? And obviously, if we assume something ahead, the resulting there is a u hat implied by that choice, right? So these beta hat and u hat, they somehow are related, right? They correspond correspond to each other. All right. So, whenever you want to find a good number, estimate, vector, whatever for this beta, 4 steps of the regression analysis are involved. So if you apply these methods later in your seminar series or whatever, it's always the same. In the first round, you have to think about the specification of the model, right? So you have to think about the variable selection. So which variable should I include, right? When we talk about methods, this is often, yeah, let's assume this is like that. In practice, this is very often a very critical question. Which variable are really interesting and important? Which variable should I include? Because we know there is omitted variable bias. And we also know that you want to have small models and not overly complicated models, right? So of course there's a trade-off. And very often there is no clear answer. No, we have some tests. I will show you some tests that help you to convince yourself and the reader and your advisor maybe that your choice of variables is okay. It's a good choice. All right, yeah, common sense, great. Okay, so, and of course, yeah, the functional form, right? Should I use really a similar, a linear model, or should I probably take the log of the variables, or should I introduce squares, or I don't know. Depends, right? If you have decided on all that, yeah, congratulations, right? Then next step, and this is then more or less a technical thing, you estimate the model parameters you're interested in. In your regression model, it's just the beta vector you're interested, mainly interested in. All right. So this is the technique. So you apply least squares, GMM, maximum likelihood, in instrumental variable estimation, whatever is necessary in your context. We'll talk about that. After you estimated it, next point is you evaluate your estimated model. You see now, if you have estimated the parameters, you know what you had is. So you know your estimated error. Yeah. And of course, if you evaluate the model you're interested in, the model fit. How well does how good does your model, your estimated model, replicate the data patterns you're interested in, right? If there's some systematic deviations, systematic errors, like in this, parametric, non-parametric picture where you might get critical, but it's a good idea to have a linear model here, right? So there are various ways to do that, depending on for what purpose your model is actually designed. Right? So whether it's something which you want to use to make policy analysis simulations, or whether it's a pure forecasting model, then maybe the model evaluation criteria look different, right? If you're just interested in forecasting, you may be not so interested in is this or that parameter plausibly signed, significant or not. You don't care, you just want to have a good forecast, right? All right. Then obviously the criteria you apply to evaluate the quality of your model looks different as if you don't want to forecast. You just have this data and you want to talk about the coefficient and the elasticities and so on, and then you're interested in the size, the parameters, if they're plausible or whatever. We can use hypothesis testing to evaluate that, right? So if the theory says this variable has no impact, then you might want to be interested in including this variable and testing with our hypothesis whether it's actually zero or not. Okay, if everything works, right, then in the end, you do work with the model, right? You apply it. And, whatever the application is in your case, right? Interpret the coefficients or maybe only the functional relationship, yeah? Use it for predictions, for counterfactual policy analysis, whatever, okay? The applications are multiple. All right. in a way, you know, whatever we do over the next months, until Feb, so it all more or less fits in these four categories, right? We always talk about how to specify, how to estimate, how to evaluate, how to interpret. Okay, that's what academic literature should do. All right. Okay, so least square estimation. This is where we start, right? So linear regression model here. That's our starting point, right? And now we want to choose beta. And you know it from the Bachelor 101 course. A very plausible criteria to find a good estimate, a good value for beta here is minimizing the squared regression error. And remember, this is very, very close to this conditional mean thing, right? We were also, in a way, minimizing the average regression error, right? So back to that. Remind you here. Look here. This is exactly now what we do. Okay. So why is it called least squares, LS? Yeah, because we choose beta in a way that these squares are minimized. And that makes a lot of sense, right? For the same reason as why we are interested in the thing, right? Because we want that our data describes the endogenous variable as good as possible, which implies that the u's are as small as possible, and small as possible means, okay, I have to take some absolute value or square or something like that, and the best way to do it is just to take the squares. We call this sum here, sum of squared residuals. And of course, it depends on beta, because whatever beta I take, the u will change, right? This is a vector, because we have k variables, right? So the technique you apply is you're actually multivariate optimization, minimization, whatever, of multivariate functions, right? Clear-cut generalization of the univariate optimization thing you know from school, right? A little bit more complicated, right? So you turn to partial derivatives, right? Because now you have not only x, like in f, x, and you have one independent variable where you can take the derivative. No, now you have k plus 1 parameters, and you want to choose your vector beta 1, 2, blah, 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 k plus 1 optimally in the sense. So you have k plus 1 first order conditions. For each parameter from j0 to k, you have a condition like that. And this is just taking the first derivative. Right? You see here already, yeah? If you take the first derivative to beta, it's 2 times this, and the inner derivation is just times multiplied with that. The nitty-gritty details I will not show in the lecture, right? They are shown in the book. We may torture Lea to show this derivation, right? Maybe he wants to do it, I don't know, right? It's a matter of taste. I would say this is just, it's just simple, boring math, right? I can do that. I can bore you here and write it down, but why should I do that? It's just in the book. There's no extra I can tell you here. As you know, now you apply this rule of differentiation, now you apply that. That's it. Okay, you can rephrase this like this, right, in matrix formula. And look, this is just u. Look here. Y minus beta is just u. So the first order conditions for the beta vector that minimizes the sum of squared residuals is equivalent to the condition that your regressor matrix is orthogonal to the vector of unobserved u's. Remember, two vectors are orthogonal when their inner product is 0. Okay? Here's not a vector. Here you have a matrix, so each of the vectors is orthogonal to u. So this is actually then, yeah, this is also a vector because you multiply a vector of the matrix of that. And again, check, when you're not sure, check whether the dimensions are okay. Look, here's x prime, right? xu is not defined. Check y. X prime, yes. X not. X prime is a transpose, right? All right, so the important note here is, or the observation, right, which we will remember when we talk about idea estimation and GMM later, and actually Michael also, right? Least square, one reason why least square is so super popular is because even if you have other idea on how to estimate parameters, in some special cases it just boils down to these squares. Look here, if you know what a method of moment estimator is, we will talk about that in chapter, I don't know, 10 or what, right, in more detail, you will see that, come on, these are moment conditions. And if I start with these moment conditions, so if I would have started not with the aim function, please use beta in such a way that the squares, the sum of squares is minimized. But if I would have said that, well, please choose beta in a way such that the errors are orthogonal to the regressors, remember that I want to have that they are uncorrelated, right? Because I don't want to have particularly large u's if x is high or low. Yeah? We talked about the point that we trust in the model. It's a good sign if the errors are uncorrelated with the regressors, right? Because then there's no systematic more. The errors should be just errors, unpredictable, random, right? It's not, x is like this, then you tend to overpredict, underpredict, whatever. No. Yeah? This is more or less this here. So you could have started with that condition, and the math would be exactly the same. So now we have the first order conditions, and you can solve for beta. So this is the first order condition. Bring this here, you multiply this out, bring it on the other side, take the inverse, and solve for beta hat. This is the formula I hope you have already seen for the ordinary least square estimator in the multiple linear regression model. Okay? That one here. This is a very, very basic formula, and usually students, when, in the course, they're interested in, what do I have to learn for the final exam? Is it allowed to have a list of formulas or something like that? And no, it's not allowed. And no, you don't have to learn formulas. There will be formulas like this here on the slides. Yeah, you don't have to learn this. This is nonsense. You have to understand them. If I show you the formula, you have to say, this is here by that, and of course it's the inverse and not because. Yeah, you should be able to understand and digest that formula. There are, however, exceptions, and this is one of it, right? I would say this should be memorized by you, okay? Because if you can't remember the formula of the least square estimator and multiple regression model, and we talk now for weeks about that, then there is an obvious problem, right? Okay, but whenever it's getting more complicated, I show you the formula, okay? All right, so let's quickly talk about the ordinary square estimator. I hope I don't bore you. Yeah, I don't know. There are some universities in Germany where there is econometrics or introduction to econometrics on the schedule, but they don't use matrix algebra because they think it's too difficult. Right? So I hope that you know matrix algebra. If not, this is, as I said already, this is the task. This is what you should do over the next 2 weeks. Yeah, refresh or learn matrix algebra. And what kind of matrix algebra? On the one hand, it's obvious from the slides, whatever you don't understand, check. And there are very good, in most econometric textbooks, there is an extra appendix or so that summarizes all the facts you have to know about matrices, right? So it's not so much, right? A few pages. And it's also not so difficult actually. If you know how to multiply matrices, it's a few things are surprising and deep, right? We could talk for semesters about linear algebra and matrices, of course, but most of the results we use, are rather suggestive and plausible. All right, come on, let's go. So what do we see here? So we say that beta hat is a linear estimator because it's a linear function of y. Look here. Given x and y, it's just you give me the observations y of your data and you just multiply it with that constant matrix. Bang. Okay? Linearity means that if I, for example, multiply y with 2, some constant, you see by the formula immediately that how this transfers to beta, right? Doubling y obviously just doubles beta. That's linearity, right? Doubling the price doubles the profit, or something like that, right? Or doubles my expenditure for the same amount of good, right? So proportionality, linearity, that's great in economics. We understand this concept. And this is reflected here in this linear estimator. Okay? Look, it's not a linear estimator because the model is linear. Two different things. The model is linear, yeah, okay, because they have linear regression, but what we're now talking about is that beta hat is a linear function of y. That's something different. Yeah? Alright, so what you see is, and that's very nice, we have a closed form solution of a minimization problem. So closed form solution means there's a formula. So it's not, the result of a non-parametric numerical optimization problem where for each y and x, the computer gives me a number and I have no clue what happens. It's just the computer says the solution is like this, okay, yeah. Maybe I see the aim function. I have to tell the computer what the aim function is, and the computer goes and there's a number, bam, right? The beauty of B-square estimation is, here's the formula, and I can use that formula to analyze the properties of that estimator. All right. So, by the way, it's a minimization problem. So, and we just use the first order condition, right? You can check the second order conditions. Remember multivariate differentiation and so optimization thing? Yeah. You have to talk about the Hesse matrix, the matrix of the second derivatives, and check whether they're positive definite or not. Ooh, right? You don't do that. But you could, right? It's a little bit, tedious, but this is the background, okay? So this is actually a minimum and not a maximum. We don't. So this is, it fulfills the first order condition, but it's not a maximum, it's a minimum. And this is shown if you look at the second order condition. All right. So, geometric properties. We talk in the next chapter a lot about the geometric properties. And this means, well, we just ignore all this randomness, right? We just give me the data, I apply this formula. Bam. Does it make sense or not? I don't care. I just apply it. I don't care how the use look like or what assumptions you just give me the data, I do it. Right? So the geometric property thing is just math. And math means here matrix algebra in the next section. Yeah? We multiply matrices and see, oh look, what happens. Right? Okay. So look, if we just talk about that formula, obviously the only thing we have to assume here in order to get a least square estimator is that this matrix here has actually an inverse. Right? First of all, right? X, the matrix X does the matrix X have an inverse? the matrix X has an inverse? No. Why not? Come on, you don't? You think the matrix X has an inverse? Do you know what an inverse matrix is? Check. You have to repeat it, because this is dramatic. This answer is dramatically wrong. Right? Yeah?
X has no inverse because columns and rows aren't aligned.
Yeah, it's not a quadratic matrix, right? The matrix X has 1 million observations and n and k, maybe 10 or 20 regressors. The matrix X is hopefully highly non-quadratic because you have lots of observations and only a few regressors. All right? Inverse matrices, however, are quadratic matrices. Only quadratic matrices where n equals k plus 1 then have the chance to be invertible. Right? But of course, there are a lot of non-invertible quadratic matrices. Maybe we can talk about that in more detail. All right, so X has no inverse. Aha. X prime, of course, also not. Because, because X prime is just the transpose of it, so it's, and if X is not quadratic, then of course X prime is also quadratic. So X has no inverse. When you write down X to the power of -1, I know you will fail the final exam. Okay? Good predictor. X prime same. What about X prime X? What is the dimension of X prime X? Is it squared? Yeah, obviously it is, because it has an inverse, right? But what's the dimension? Yeah?
N times k.
No, n times k is x. X prime x has an inverse, so it's quadratic. So it has to be 5 times 5, 3 times 3, quadratic. Right? Yeah?
N times n.
No. Just the other way around. It's
K plus 1 times
k plus 1 times k plus 1. Look, it has to be like this, because in the end, on the left-hand side, there's a k plus 1 vector. So somewhere, the dimension here is n. You multiply that with x prime, and this makes it to a k vector. And now you can multiply that k vector to this k times k, or k plus 1 times k plus 1, k matrix, and this gives you the k plus 1 vector. This is why I say it is a good check for you if you remember, if you write down the dimensions of these guys here and check whether it fits all together. Right? Okay. Okay, so all I want to have to assume is that this here is invertible. And now we know, you should know, what are these matrices, these quadratic matrices where the inverse exists. We talk about that in a minute, right? But this is the algebra I would say you should know. Okay, the point that is here emphasized is that if you give me just the number, if you just give me the data, and I tell the computer, please calculate the corresponding beta hat, this is obviously a number, right? The computer gives you, bam, the number, a vector, actually, of numbers. Okay, and theoretically, it's nice to distinguish between these two concepts. One thing here is we call the estimate beta hat. Now this is the number, the concrete number vector that results from a concrete data sample. Right? And this can be compared or somehow confounded with the estimator beta hat. And this is a formula. This is the function, the way we calculate it. Right? In German, we call it the Schätzfunktion, right? So it's just the general formula, that's the estimator. So we talk about the properties of an estimator, then we talk about this formula here. And if we talk about the estimate, then we have a complete data sample and look at the numbers that come out. Yeah? And if you talk about the estimator, then you recognize that actually that beta hat will be a random variable, and we will talk about that in 1.3. Yeah? Here we are. Okay, so one slide. So now we talk about the geometry. It's called the geometry of linear regression, and you will see immediately why that's a good title. So here you see somehow an overview or summary of that, right? This is our starting point. We now talk for the next weeks or so, I don't know, about the linear regression model and the ordinary least square estimator. Please recall, there will be later a generalized least square estimator, a GLS. Yeah? Ordinary least square estimator. Sometimes I forget the ordinary, I just talk about the least square estimator, and then I mean that one, right? We will talk about generalized least square estimator later. Okay, so that's the formula for the ordinary least square. And what we already discussed is that this formula always exists, not a problem of the computer, if this matrix here is invertible. And what we've already seen here is that not only the use, but what you can easily check here is that also the estimated errors you had are always orthogonal to all regressors of x. So like these theoretical moment conditions that the theoretical unobserved use are orthogonal to x, this is obtained by the square estimation for the estimated u hats. And look, that's the proof. X prime u hat is x prime, and this is just u hat. That's the definition of u hat. You multiply it out, you get, you insert what you know about beta hat. Beta hat is this here. So x prime beta hat is that one. Ooh. Now you multiply it out. X prime y, x prime that, and you see that this cancels out here. X prime x times x prime x inverse cancels out. It remains x prime y, 0. Proof check. Most of the proofs we use here over the next weeks are like this. Right? Just plugging in, multiplying out, ready. Sometimes it's much more complicated than this, but in the end, that's what you need to know. Okay, so final slides for today. The assumption of x prime x is invertible, right? This is our matrix x, right? And you can show that this x prime x matrix is invertible if and only if all the columns, all the rows, which is the same, are linearly independent. Or, as it put it here, if they are not collinear or perfectly collinear. Right? So if this matrix here has, and this is again an alternative way to put it, has full rank, and this is would be k plus 1. If this matrix here has rank k plus 1, so if there are k plus 1 linear independent rows here, then x prime x has an inversion, has an inverse. Okay? This follows from very basic conditions about the rank of a matrix and the rank of a product of matrices and so on. Okay, so if this here does not exist, that means that some of these regressors here are linearly dependent. And the most simple example is, suppose you have two identical regressors here. Yeah, you apply R, but for whatever reason you type in the same variable twice. You name it differently, to fool the computer, but it's actually exactly the same variable. What will happen? Estimate. Error will happen, hopefully, right? Because R wants to compute x prime x and it doesn't exist, right? Because you plug in two identical regressors, therefore if this is identical to that, then the rank of this is k minus less than k, meaning implying that the inverse does not exist. All right? So, time is running out. We talk more about this and the rank of matrices, and here I thought we talk also about today about this, but this we will do next week when we talk more about geometry of linear regression. Thank you for coming. Go to the tutorial, repeat matrix algebra, and we see us next week.
Just by, so easy. Okay.